artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hello and welcome to episode 311. Studying human intelligence is a matter of neuroscience, and creating software is a matter of computing. So creating artificial intelligence would be at the intersection of those fields. It's called computational neuroscience, and I have with me today one of the founders of that field. Tomaso Poggio is the Eugene McDermott Professor in the Department of Brain and Cognitive Sciences at MIT and the Director of the Center for Brains, Minds, and Machines. He is a Fellow of the American Academy of Arts and Sciences and of the American Association for the Advancement of Science, and a Founding Fellow of the Association for the Advancement of Artificial Intelligence. His homepage says that he develops models of brain function that illuminate human intelligence and builds intelligent machines that can mimic human performance. Wow. Tomaso is going to define computational neuroscience, and then we're going to talk about computation in the human brain, how large language models landed for him, holography, limitations of LLMs, and backpropagation equivalents in the human brain. So there are some things we're going to mention that it would be good to define in case you're not familiar with them, like backpropagation. These definitions will be overly simplistic, but if you already know where they break down, you don't need them anyway. Backpropagation is part of how an artificial neural network is trained. By looking at the answer it gives to a question, which will be wrong to begin with because it starts out with random weights, and then adjusting the weights in the network, working backwards from the output layer to make it a little more likely to come up with the right answer next time. Then repeat that a few billion times. A Turing machine is a hypothetical device described by Alan Turing in, this is amazing, 1936. Not having any actual computers, he had to imagine one, and he described a device that could read and write marks on an infinitely long paper tape and move backwards and forwards over the tape. And it had a set of rules that describe, given its current state and what's under the reading head at the moment, what it should do to the tape and which direction to move. Sounds a lot like a very primitive digital computer, except for the infinite part. And Turing proved mathematically that this device could compute anything that was computable. So it became a very handy thought experiment device, because if you could show that another device could do what a Turing machine could do, you knew it could compute anything. That leads into compositionality, a term that means that complex things can be broken down into a set of simpler things, which is basically how all software works, by translating a hard problem into a set of instructions. Emergence is something we've mentioned on the show before. It's a fancy word for the principle that the whole is greater than the sum of the parts. And so, for instance, the human brain has a lot of very simple parts called neurons, but put enough of them together with simple rules and they can compose a limerick. Most of them anyway. World models are the goal of modern robotics. They're AI models of the physical world that enable a robot to know about, say, gravity and donuts being squishier than tennis balls. And gradient descent is an algorithm buried inside AI training programs that just needs to figure out the lowest value of a function. But because the function is so big and complex and multidimensional, all it can do is land on some random place in the function and then see if it can find a lower value. As long as it can keep going downhill, descending the gradients, it does that. And that's a neat algorithm. When it's finished, it means it's found a minimum of the function, which is what it was looking for. It's not necessarily the global minimum, which would be ideal, but at least it's a local minimum. And holography is a way of using lasers to store and replay 3D images of a scene in a translucent plate, i.e. hologram. And it has the neat property that every part of the image is stored in every part of the plate. So if you break it up, you can still get the whole image from any one of the pieces, just somewhat degraded overall. Okay, so that was a lot of exposition, but I hope it helps you as we get into the interview. Tomaso Poggio, thank you for coming on AI and You. We are here to talk about computational neuroscience, a field that you are credited with being the father of in some circles, how, as a proud dad, would you describe to us computational neuroscience?
Well, I guess a simple way to describe it is to think of intelligence as a property of computation. So if we want to study our intelligence, I think we have to look at it from a computational point of view. If you want to study intelligence in machines, computers, same thing. We have to look at it from a computational point of view. I think a very nice, superficially simple, but actually quite deep definition of intelligence is what Turing gave, the Turing test or the imitation game. Say a system, a machine, or a biological organism is intelligent if another system cannot distinguish it from itself, like a human, in the example of Turing, interacting through a teletype at a time with something in a room. If after an extended conversation could not distinguish what was inside from another human being, then what was inside was as intelligent as a human being. And this is really based on the idea that if something is indistinguishable from something else, then for all purposes is equivalent to this other thing. It's a deep concept, and a postdoc of mine has recently extended this in a very interesting way. You can say that a machine A is more intelligent than a machine B if A can imitate B in all purposes, because that means it would be at least as powerful as B. There are a lot of subtleties there, but it's interesting that the Turing test deep inside has a lot of connection with some of the deepest problems in computer science, including cryptography. So I find quite interesting to take it seriously as a definition really of intelligence. And of course, at the basis of it is intelligence as computation.
Right, which brings up the other thing, one of the other things that Turing is known for, the Turing machine, the abstract model of computation. So are you saying there, or is it a tenet of computational neuroscience that what the human brain does could be expressed as a Turing machine?
Yes. This is where in the realm of tautologies, in a sense, but the idea is really that this is the Church-Turing thesis. It's not a theorem, it's kind of a statement that everything computable can be computable by a Turing machine.
Right. But that's, to be clear, then you're saying that what goes on in the human brain is computable.
That's right. And I want to make some caveats right here. We have done some other work that suggests, actually these are mathematical theorems, that if you have a compositionality, which is something you certainly have in language and in most of mathematics, then this is equivalent not only to Turing computability, but to efficient Turing computability, meaning can be computed in essentially reasonable time. Now, it's rather natural to think, to conjecture, that the part, that the activity of our brain that we certainly deem intelligent, like producing language, like programming, like proving theorems, is compositional and therefore efficiently Turing computable. On the other hand, the parts of our brain that are evolutionary older and underlie traits like emotions, what we call instincts, that may not be compositional and may not be efficiently Turing computable. It just may. I don't think it's the case, but I think it's a little bit more difficult to make a claim that those products of our brain can be efficiently computable. Maybe they are not. Unlikely.
Is it a goal of yours to find out the answer to that one day?
Yes, in principle, though I think it's a difficult one. I still have not found a way to do it. I'm just saying that it could well be that we can represent the parts, as I said, the kind of linguistic parts of our intelligence in terms of not only a Turing machine, but something that can be computed by a computer in a reasonable time. And that to do the same for emotions may be more difficult.
Mm.
I'm not sure how to prove that.
Now there is an understatement, or there's a statement of a grand unknown in human science at the moment. And kudos for taking on such a grand goal. I'd like to explore the ways in which AI and human cognition illuminate and contrast with each other. Because today's AI's neural networks at their base look superficially like they're based on human cognition because they've got this model that was derived from noticing that the human brain had all of these neurons connected that signal each other. But then it seems that that parallel halts. The human brain doesn't seem to do backpropagation the same way. There's all kinds of algorithms that we use for making these neural networks work that isn't based on what happens in humans. Can we look at this? Can you say, what are the ways in which AI is most like and most unlike human cognition?
Well, AI is based on digital computers. And certainly neurons are not doing digital processing. But apart from this, if you just look at the hardware of our computers, our digital computers, and the wetware of the brain, there are a lot of big differences. First of all, speed. There is a clock in our digital computer, and this is now a gigahertz. But in the brain, there is most likely no clock, maybe something like local clocks in some part of the brain, maybe, but certainly no general clock. And nothing happens faster than 1 kilohertz. So 1 millisecond is the fastest you can get in terms of some of the neurons in the brain, these sudden changes in electrical potential that are called spikes, and they last about 1 millisecond each. And at synapses, the contacts between neurons, you have also about 1 millisecond in terms of the time constants involved, which is much, much slower than our digital computers. On the other hand, in our digital computer, the basic units of computation, transistors or logical gates, have typically like 3 or 4 wires at most, connecting them to other elements in the computers. In our brain, there are synapses for each of the neurons that are hundreds, thousands, several thousands. So the connectivity is much higher, and that's probably how the brain corrects for the slow pace of its pseudo clock. So these are already big differences. And now in terms of, the architecture it looks like, so sensory modalities like vision have an organization that is quite similar to convolutional deep networks, but we don't know really very much about the architecture used for producing language and producing thoughts. Almost certainly, we have language is not a condition for thinking, for reasoning, and also evolutionary. It's very likely that sophisticated thinking came before language. So we have this paradox because large language models need the language actually to be trained. They're trained on human language to start with in predicting the next word. But in terms of human intelligence, it looks like intelligence came before language. Evolutionary was very likely developed to communicate first. So the path to intelligence is different, evolutionary, for humans and for machines. So some of the big picture.
When those large language models came onto the scene in a big way, end of 2022, what, if anything, surprised you about their capabilities? That were they going beyond what appeared possible at that time with what could be done with modeling text, as you say? Were there any emergent properties of these large language models that surprised you?
Well, I think I was very surprised, and I know a lot of other researchers like me were surprised by how powerful was training on the next word. Obviously, predicting the next word may require, in a sense, understanding what's going on, understanding what you're speaking about. But still, I would have expected a system like this to produce fragmented concepts, not just the kind of consistent answers that we can get from large language models. And of course, there is more than predicting the next word. That's pre-training. Then there is the post-training of these models using techniques like reinforcement learning or more recently evolutionary algorithms. But still, I was surprised by the consistency of the answers. I think of a large language model in the most simple way as kind of associative memories that associate, for instance, next word or next words to the preceding words. And I've been always a kind of a fan of associative memories. They were introduced basically in the 60s, at the time just as memories, but with architecture that were very similar to shallow networks. I'm thinking in particular of a paper by Christopher Longe-Higgins and David Wilshaw in Nature, and that the goal was to have a network that could associate vector A to vector B.
Is this word to vector? Do you know the one I mean?
Yeah. Well, this is much earlier. This was 1969. And what they were trying to do is to have a network that could do something similar to holography. In holography, one thing you could do, and this was kind of fashionable in the early 60s, was to record the image of object A with a reference beam, a laser, shined on object B. And then by presenting object B, you could retrieve object A. That's a nice property of holograms. And you could store many pairs of A and B, A1, B1, A2, B2 on a hologram and selectively retrieve A10 by presenting B10. So they were trying to reproduce that in a network of basically binary neurons, and they came up with a scheme which is very similar to a one-layer neural network of today. This was 1969. The emphasis then was not in prediction, was memory, but the same network can do prediction, of course. If what you present is not exactly B10, but some approximation to B10, instead of A10, you'll get some approximation to A10 back. So that's what neural networks do today. So in a sense, you can think of neural networks and transformers as a kind of associative memories, associating, in the case of transformer, a sequence of tokens, a sequence of words, to a specific word or a small set of words. And of course, if the sequence is not exactly the same, you will get an output which is not exactly the same, but similar to what it should be. But if you think in this way, at least in my thinking, you could imagine that this system could work, but was kind of not obvious that it could give you a consistent sequence of words instead of just fragments for every sentence that you were producing as input. And so I was personally quite surprised by how powerful, if you want, how consistently powerful this was.
Here we are having a conversation using language. The kind of things that are going on in my mind are understanding what you're saying, correlating it with other things that I know about or want to know about in this field, looking at my notes, trying to decide what the audience is taking away from what we're talking about at the moment, a whole host of things that come together to shape the next words that I'm going to say. And I think of that as being a process of reasoning and using intelligence in some way. And you're doing the same kind of thing. Now, if we distinguish that, if we contrast that with a large language model, which has not been trained on anything except text, but has been trained on far, far more of it than any human is ever exposed to, so that it's able to go beyond and do these kind of emergent tricks that look like, and in some cases exceed, what I'm able to do with the process that I just described to you. If you compare what's going on in the human mind versus how the large language model is doing that, do you see fundamental limitations, for instance, to the large language model? Would you say, look, you can only drive this so far before you're going to hit a wall, and then you're going to have to come back to the drawing board and follow some other principle in neuroscience? Would you offer that kind of counsel to the AI scientists?
Well, yes. I think that obviously, because of what I mentioned before about evolution of intelligence, I think it's likely that our own intelligence developed in terms not of language, but probably motor control and simulating the physics of the world. Now, it's a bit unclear how much you gain if you want to repeat with machine the same evolutionary development that our own intelligence had. It's quite possible you can bypass it through language. Now, personally, I think that you can bypass using just language quite a lot, much more than I would have thought if you'd asked me 5 or 6 years ago, but probably not so much in terms of motor control, for instance. So for robotics, I think you really need to go beyond language. And people are doing this and finding, there are certain limitations to use just language for robotics. But again, I don't think this is a fundamental limitation because you could still use the same underlying algorithms, basically transformers. You are dealing with sequences in language and also in motor control. So you can, in principle, use the same architectures, transformer-like or diffusion models like for motor control. It's an open question, I guess, how much you can gain by bypassing language. I think people speak about word model. These are kind of fashionable these days. But I think that's probably a bit exaggerated because the underlying algorithms of essentially predicting, dealing with a time series remain the same. And the language is quite powerful. So what I always think is that we have already now a kind of large variety of slightly different forms of intelligence. And I'm sure that our own intelligence, because of the different hardware, because of the different evolutionary path, is not the same as the one that we have in large language models. But they're both intelligences, but possibly roughly at the same level. They're just different forms of intelligence. And it's not a question of, for this specific discussion, whether one is better or worse than the other one, but they're just forms of intelligence. They will pass a Turing test in both of them, but they're just quite a bit different, like we have different genomes for different forms of lives. And I think studying these different forms of intelligence can tell us a lot about intelligence in general, what are fundamental principles of intelligence, like studying the genome of the fruit fly, comparing it to our own genome, has taught us a lot about biology.
and looking at genomes and the human hardware, incredibly complicated wetware that forms naturally through result of gestation and the human body growing up. And a lot of what we do in cognition is shaped by that hardware. We have this kind of simplistic model that the brain is the hardware and the mind is the software, but there really seems to be a lot of firmware in the brain, and that it's born knowing how to do a whole lot of things that are essential to survival. So how much of computational neuroscience hinges on trying to figure out what that firmware is?
Yeah, I think it does quite a bit, to emphasize the point you just made, and also something you said before about backpropagation. I think one of the mysteries, potentially quite important, is the following. In the intelligence system that you are making, large language model and so on, a basic tool has been gradient descent, backpropagation for supervised training, and variants of it, like stochastic gradient descent and Muon and Adams. Now, there seems to be no plausible substitute for backpropagation in the brain. Just because of how neurons and synapses work, it's very unlikely that they can support something like backpropagation. I think one big contribution to computational neuroscience, and potentially at the same time to AI, would be to discover a mechanism, if it exists, that does what backpropagation does for artificial networks. We've done some work recently in my group that seems to suggest that plastic synapses can do something different from backpropagation, but essentially equally important for supervised learning. But we don't have any real experimental validation of that. If this were to be validated, I think this would be a very important contact point between AI today and neuroscience. At the level of a basic piece of, it's between hardware and software. And we'll see. But I think this one of what are the learning algorithms in the brain is a key problem for neuroscience right now.
And that's the end of the first half of the interview. We'll have the next half next week. In today's news ripped from the headlines about AI, Mitchell Katz, CEO of New York City Health and Hospitals, announced that he is ready to replace radiologists with AI in some scenarios and called on fellow hospital CEOs to push for changes to New York state regulations allowing AI to read images without a radiologist. David Lubarski of Westchester Medical Center said at the same forum that AI already deployed in his system is, quote, actually better than human beings at breast cancer screening, with a false negative rate of only 3 in 10,000 for non-high-risk women. One Brooklyn Health CEO, Sandra Scott, called it a game changer. Now, this doesn't mean we're about to see the fulfillment of Jeff Hinton's prediction of AI putting radiologists out of work, but it does mean that a lot more radiology can get done faster, and that's a good thing. Next week, we'll conclude the interview with Tomaso Poggio, when we'll talk about learning in the brain and synaptic mechanisms, the role of sleep, what AI scientists should pay more attention to in neuroscience, other computational mechanisms in the brain besides neurons, connectomics, robotics, and flies and worms. That's next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.